Now let's talk about forces and Newton's laws of motion. Before that, we have to define a force. A force is a push or a pull, or it is an interaction between two bodies, and it's not a property of any body or an object. And there are two types of forces, the contact and non-contact forces. When I say contact forces arise from physical contact like tension, like friction. Then action at a distance forces, it's from the term itself, it's at a distance like the force of gravity or the force of a magnet or electrical force. Now, if we are going to describe a force is a vector quantity, and we can use arrows to represent a force. And the length of the arrow is proportional to the magnitude of the force. As you will notice here, 5 Newton, this direction, because a force is a vector, and this much in terms of its magnitude, and also 15 Newtons also represented by the length of the arrow, having that magnitude 15 Newtons. And mass, you have also to know what's a mass. As a review, it's a measure of the amount of stuff contained in an object. So it's the amount of matter. And this is very important in Newton's first law, because Newton's first law is stated that an object continues in a state of rest or in a state of motion at a constant speed along a straight line unless compelled to change that state by a net force. And the net force is the vector sum of all of the forces acting on an object. In other words, Newton's first law tends to continue in its state, either if it's at rest or in a constant velocity motion. So this is what we call as inertial frame later on. And take note, unless compelled to change by a net force. When I say a net force, it is the summation of all the forces acting on the object. If we are going to elaborate what's a net force, so if you consider the individual forces in an object, so like this, we have, in this case, we have here the force diagram. So in this case, we have the 10 Newton here, and we have also the 4 Newton here. So if you want to get the net force, you follow the tip to tail method. If we draw the 10 Newtons, this much, okay, you draw it, and then co- uh, you put another drawing to represent the second force like the 4 Newton from the tip of the first vector, okay, tip to tail method. So here, and this is the tail of the second vector, 4 Newton in that direction. Okay, sorry, assuming it's a straight line. So if it's 4 Newton here, so, and this is 10 Newtons. So in other words, if we are going to have the sum, okay, if we review, we have the sum in a tip to tail method from the tail of the first vector to the tip of the last vector. So that's why this is 6 Newton here. And this represented by this in a form of net force. Okay, so that is how a net force is being determined. Okay, let's proceed. And if your forces also, like they are not on the same axis, one of the forces is in the y and the other is in the x, so you can also do this by tip to tail method. So like if you draw still this 4 Newton here, so this 4 Newton, and then I will have the other force. Let me use another color. So if I have another force, 3 Newton going to the y, so if from that, so this 3 Newton for example, and I want to get the resultant. So it's still the same thing from the tip of the first, or from the tail of the first to the tip of the last vector. So here, this is your resultant. Okay, so this is now achieved by the Pythagorean theorem. So this is the resultant force. So some will use FR. Okay, so to have the resultant force FR, take note, this can be achieved by the Pythagorean theorem. It's the square root of the square of the legs, the sum of the square of the legs. So like 4 Newton, you square it. These are the legs of the right triangle plus 3 Newton, you square it. That's why you will get 5 Newton, because this will give you square root of 25, which is 5. newtons. Okay, carry out unit. So that is why you have here the net force of 5 newtons. And then how to determine the angle? The angle is determined by the ratio, the trigonometric ratio that you are familiar with. So if you still remember, so the angle is here, and take note, it's with respect to the x-axis. Okay, if this is y and this is x. So if this is theta, the given is 3 newtons and then 4 newtons. So it's the opposite side, and this is the adjacent side. So therefore, it's easy to use tangent theta in this case, which is the tanawa, opposite over adjacent, 3 newtons over 4 newtons. And if you want to get the theta, you get the inverse tangent. So inverse tangent, and then this is 3 newtons over 4 newtons. And obviously, if you have in your calculator, it's 64 degrees. And take note, have the degree mode in your calculator when you are computing this way. Okay, so that's how to get 64 degrees. So to get the summation of a vector, you use the Pythagorean theorem and also the trigonometric function. Okay, so let's proceed. And if we clarify inertia, inertia is the tendency, natural tendency of an object to remain at rest in motion at a constant speed along a straight line. And it's measured by its mass. So the mass of an object is a quantitative measure of inertia. And the unit, the SI unit of this is in kilogram. Then an inertial reference frame is one in which Newton's law of inertia is valid. This is true for the state of wherein the object is at rest or moving at a constant velocity, meaning inertial frame is the one with zero acceleration. So this inertial frame refers to zero acceleration. And accelerating frame, of course, they are non-inertial if it has accelerated already. So acceleration can be achieved by changing the magnitude of like the velocity, or changing the direction, or changing both the magnitude and the direction. Okay, so that's to clarify that first law is only operational for the state wherein the object is at rest or moving at constant velocity. Okay, and Newton's second law. So Newton's second law is in terms of the force, mass, and acceleration. So mathematically, the net force, it's describing the net force. In this case, it's using the symbol sigma. And take note, the force is with an arrow on top because force is a vector. Okay, the sigma means the vector sum. And this is how it's stated, Newton's second law. When a net external force acts on an object of mass m, the acceleration that results is a magnitude that is inversely proportional to the mass. The direction of the acceleration is the same as the direction of the net force. So both force and acceleration are vector quantities, and they must have in the same direction. Take note of that. So in this case, this is how it's stated, the acceleration here. If you have noticed, the acceleration is directly proportional to force, and whatever the direction of this force is the same direction of the acceleration, and it's inversely proportional to mass. So that is in your activity on Newton's laws, in which you have greater mass, the lesser will be the acceleration. And if you are going to solve for the summation of the force or the net force, so it is equal to ma. But originally, it is stated in terms of the acceleration. Okay. And uh, for the SI unit of force, so if you have noticed, force as derived is equal to MA, right? So if it's equal to MA, so this is the unit of mass, and this is the unit of acceleration, so kilogram and meter per second squared. So this is kilogram meter per second squared, and this is in unit Newton. Okay, so take note that in physics it's important to always carry out units in problem solving, because this could mean a different kind of unit. So for the unit of mass and acceleration to become Newton, it must be in kilogram and meter per second squared. Okay, so remember that. And these are the other units. In the SI system, Take note, we have kilogram for the mass and meter per second squared for the acceleration, so the force is Newton. For CGS or centimeter gram second system, the mass is gram and the acceleration is centimeter per second squared, and the force is dyne. And then for the British English, slug for the mass, and then acceleration is foot per second squared. Uh, British English is otherwise having shall we say, it's a FPS system. So it's an FPS system, this one. It stands for foot, pound, second. Because it's using the foot here, okay, second squared, and the unit of force is pound. Okay, so that's for all other units, non-SI unit for the concept of force and having acceleration and mass. Okay, now in Newton's second law, it's important to draw a free body diagram or FBD. So what is a free body diagram? So a free body diagram is a diagram that represents the object and the forces that act on it. So this is what we call as FBD. So these actual forces acting on a body is a force diagram. So you can convert a force diagram into a free body diagram by having the object as a dot, and usually it's at the origin of the coordinate axis. So like if there are two forces acting on this direction, positive x 275 newton and 395 newtons, so you can have it here. Okay, the 275 and the 395 newtons. And another force which is opposite here, which is 560 newtons, so you can also draw that way. So this is the free body diagram. You represent the object as a dot to represent its center of mass. Okay, this is important in problem solving because if you want to get the net force, so it's clear that you can add all the forces acting on x and all the forces acting on y and use the appropriate trigonometric ratio. Okay, so here, if you want to get the net force, so like they are in the x-axis, so all you need to do is just to add them and then affix their signs. If it's towards the negative x-axis, so it's negative. So in this case, like 275 newton is to the right, plus 95 newton is to the right as well, minus 560 newton is equal to positive 110 newton. Why minus? Because this is supposed to be plus, okay? This is supposed to be here plus. Okay, this is a plus here. This is a plus, and then minus 516 newton. Okay, and plus minus can become negative because why minus 516 newton? It's in the x direction, negative x direction. So this is negative 516 newton. And of course, they're all in x, so you can add. So it's directed along the positive x axis. So the net force is still along the positive x axis of the coordinate system. So that is how to add forces if they are all in the same line. Okay, so next. Yeah, like if there's a caution, you have determined the net force. So if the mass of the car is 1,850 kilograms, then by Newton's second law, the acceleration is. So by Newton's second law, acceleration is summation of all forces divided by mass. So therefore, it's 0.059 meter per second squared. Okay, so just manipulate it. And why the unit is meter per second squared? Take note that the unit of Newton is in this case kilogram meter per second squared. So we can cancel out kilogram, and what is left is meter per second squared. So that's how important unit is in problem solving, especially in physics. Okay, so um, okay, we'll proceed to the next. Okay. Take note, it's emphasized that the direction of the force and acceleration vectors can be taken into account by using x and y components. So here, summation of f can be along the y and along the x, and it's equal to may, and for the component of force along y, the summation, and for the component of the force along x, it's max. So take note the x for the acceleration, also x for the force, because they would have the same direction, or the same force and acceleration have the same direction as vectors. Okay, so like a problem in the book Cutnell and Johnson. So we have here a guy paddling here using a boat, and the forces are shown here. We have 15 newton. There's a 15 newton force, and there is a 17 newton P force. So if you want to have the free body diagram of that, so you have here the origin, okay, as the body, as the raft or the boat, and then 15 newtons and 17 newtons are the forces. Okay, and if you want to get the summation, you do the uh, method of adding vectors through component, or if you wish, you have the tip to tail or the parallelogram method. Okay, so how? In this case, you have to break the forces into x and y components. So if you refer previously, P force is along x only. So take note the P force is along x, and the A force is having 15 Newton magnitude, but take note it has an x and a y component. So let me have this. Okay, have you noticed this one? The one here. Okay, so this is the A, the one in broken line, and these are the components. Okay, because if this is 67, okay, I want to use. Okay, so yeah, so here, if this angle is 67 here, okay, 67. Okay, here. Take note that this is adjacent, and this the A here is the hypotenuse. So this is the A hypotenuse here. So therefore, this is the cosine. Supposedly, it's written as cosine 67 equals cosine 67 equals, diba, adjacent. So this is a adjacent. No, it is cosine 67. It's adjacent, which is in this case a along x. Okay. For all, let me clear so that okay. Okay. So if I will draw another one, so like um, this is your A, and here this is your AX. And instead of having the AY here, I will draw AY here because I can just transfer it AY. Okay, because here it's the AY here, and this is the AX here. Okay, I can transfer the AY to the other side, so that it can form a complete triangle, and this is still 67. This is still 67 degrees. So therefore, if you want to get the AX, so it's cosine 67 degrees equals AX over hypotenuse. So hypotenuse is A. So that's why if you want to, if you want to solve for this AX, AX is equal now to A cosine 67 degrees. Okay. Hello, Alexis. I'm still having this for a screencast. I'll be posting this video later on YouTube. We will start by 10:30, right?
Yes, sir. Sorry,
10:30.
sir.
You're just early. It's okay. It's okay.
Yes, sir.
Okay, so I'm just recording again so that I can post it in YouTube. Okay, and we will have another lecture on 10:30. Anyway, you can just see that one. I am uh, figuring out how to present it. Okay, it's okay. So in this case, it's cosine 67 AX over A, and then AY is opposite, so we can have the sine 67 degrees is equal now to AY over A. So if you have to solve for AY, you have A times sine 67 degrees. Okay, so this is A here, which is the vector itself, the 15 newtons. Okay, so this is how to figure out the components of a vector and have it in a summation, like along x and along y. Okay. Thomas, I'm just having a screencast for this, and I'll be posting this video later on YouTube. So our class will still start at 10:30.
Okay.
Okay. So Okay, thank you. And the net force on the raft, it's how to get the forces here. It is having the x component, so and then the y component. So 17 newtons and 0 newtons here. And for the a, it's 15 newtons and cosine 67. Of course, you use your calculator and then 15 newtons sine 67. So you add all the x component and you add all the y component. So you have 23 newtons and 14 newtons, and you can plot it in the x axis or in the coordinate axis. So since your x is positive, so it has an ordered pair of positive and positive. So it's in quadrant 1, and you know how to plot it. 23 newton in the x and 14 newton in the y. So you can plot it and have, like, for example, have another like this vector. So you can have the summation, which is the resultant, and you can have also the components along y and the components along x, and figure out also the um, trigonometric functions. So that's how to apply your concept of vector addition using the component method in this having summation of forces in Newton's second law. Okay, so let's proceed. Okay, so for this, if you are already having the 23 newtons for the x and the 14 newtons for the y, you can solve also the individual accelerations along the x and the y. Take note, the acceleration along x, it's also having the same direction of the force along x. Excuse me, and also the force along y, it's having the same direction along the force of the force along y. So in this case, 23 newton as previously solved, so this is already solved, and then this 14 newton, and of course you use the common mass, the mass of the raft with the boatman. So in this case, you have the 0.018 meter per second squared on the acceleration along x, and the acceleration along y also. And you can also still plot that one in the coordinate axis. So it's in quadrant 1, and figure out what's the angle and what's the summation of the acceleration. Okay, so still use the Pythagorean theorem and the tangent or arctangent function. Okay, so if we proceed, let's have the Newton's third law. So the Newton's third law of motion, as otherwise, is the law of interaction. Whenever one body exerts a force on a second body, the second body exerts an oppositely directed force of equal magnitude on the first body. So whatever you like, if you slap the other person's face, so the other person feel that force, and also your hand feel the force from the face of that person. And how do you characterize the forces? They are equal in magnitude but opposite in direction. So take note, they are equal in magnitude but opposite in direction. So how can that be equal? Like a common example. Um, having a car, like you have a very large object. So here, for example, you have the car, and then we have a mosquito. Okay, like a mosquito going that way, and a car also going that way, and the car is having a very large mass. So they can be equal. Their forces are equal, and still the car will not be like moved because of its huge mass. So the car is having a huge mass, and the mosquito is having a small mass. So take note, the force is equal to ma, right? So if it's ma, it will be compensated. It will be compensated by its acceleration. So therefore, if the car is having a greater mass, so the acceleration is very small, and your mosquito is having a small mass, so the acceleration must be very large. So they are still equal. So in this manner, the forces are equal in interacting in the interaction, but the acceleration will not be equal. So they compensated with the mass and acceleration. Like in this example, a magnitude of force is 36 newtons. Okay, this person, if the mass of the spacecraft is 11,000 kilograms, so 11,000 kilogram ang spacecraft, and the mass of the astronaut is 92 kilograms, then what are the accelerations? So either you use this one because you have given masses. So you can solve using the Newton's second law still, F is equal to ma, uh, applying it in this Newton's third law. Okay. Okay, so We have that. So on the spacecraft, yeah, it's F is equal to P, and then on the astronaut, still F is equal to negative P, yeah, opposite. So if we use the P there, 36 newtons divided by the mass of this spacecraft, 11,000, so 0.0033 meter per second squared. But for the astronaut, because the mass is only 92 kilogram, and of course it's in the opposite direction of force, so it's negative 36 newtons divided by 92 kilograms. So take note it's opposite. So the negative p here. So this one. Okay. So it's negative p. So it's opposite. Okay. And here, negative p over ma. So negative 0.39. So they have different accelerations, but their forces are still equal, opposite in direction. Okay. And in nature, there are two general types of forces, fundamental and non-fundamental forces. So fundamental forces are as follows: gravitational force, strong nuclear force, we have electroweak force, and electroweak force. Okay, and we will discuss these fundamental forces later in physics. And non-fundamental forces: friction, tension, and rope, and normal or support forces. So that's an overview for now for the Newton's three laws of motion, and I'll be posting this one in the YouTube.